Hey, welcome to our short and sweet series as we try to give you a real quick overview and a concise presentation on a bunch of famous, popular calculus topics. Today, we're going to look at improper integrals, and we're going to break this into a two-part series. Today, we're going to look at what we call part one, where we have an infinite bound. In our part two video, we'll look at what we call infinite discontinuities, where we've got some vertical asymptote at either the left endpoint, the right endpoint, or somewhere on the interior. But anyway, we'll save that for the next video. So today what's going to happen is we're going to talk about, what happens if we have an infinite bound here, or maybe we have negative infinity here, or maybe you have a combination of both of them. And basically the process is the same no matter where you see that infinity sign. We're going to rewrite the definite integral in terms of a limit. Now, what's really crazy about these improper integrals is, well, first of all, the foundation of, like any other definite integral, f of x, the integrand, has to be continuous, okay? Doesn't have to be differentiable. It's just got to be continuous. And as long as that's the case, then this definite integral is going to measure the area bounded between that function and the x-axis. But what makes these so interesting is this little sliver continues forever and ever and ever. And ultimately, at the end of these problems, we have to make a decision on whether these integrals converge or whether they diverge. The idea of being convergent means that we end up with a real answer, okay? Which, when you think of that, that can really boggle your mind. You're thinking, I've got this region, and on this right side, this right tail, it never ends, but yet I come up with a finite amount of area. And I guess the best explanation I can give you is that this f of x function is going to get so close to the x-axis that the area between them is so minuscule and negligible that it doesn't impact the entire answer. If you've studied infinite series yet, you've seen where the sum of an infinite number of terms could actually equal a finite real answer, and the same concept kind of creeps in here. Or, of course, if the opposite of convergent is divergent, so if you don't get a real number for your limit, then the answer is going to be divergent. And a lot of times, basically, that's going to happen whenever this f of x function stays further away from the x-axis. It still may trend towards it, but it's at a very slow rate, and the gap between them is large enough that we have infinite area. So as we look at okay, here's our definitions or ideas on convergent, divergent. Again, if that limit exists, we say that the improper integral converges, otherwise it diverges. And here's our first live example. Okay, this is a really fun one for a couple of reasons. So anyway, your first move is just to really take pride in having great notation and rewriting this integral in terms of a limit. And now we're going to try to actually come up with the antiderivative. This is a very sneaky one. There's not many prodding hints that we can offer. We're going to see this as an arctan, where your u is equal to x and your a is a nice 1 in this case. So we're going to get the limit as b approaches infinity. The antiderivative is the inverse tan, or the arctan, from 0 to b. So we're first going to substitute the b. So we'll try to evaluate the arctangent of b here in a second, and then we'll substitute the 0. And this is a really fun limit to think about. And I think for me, it all comes back to, can I visualize that graph? And when you graph the arctan function, it looks like this, with its first asymptote is at negative pi over 2, but then this asymptote is at pi over 2. So the graph, as x gets bigger and bigger and bigger, the graph itself is approaching a height of pi over 2. So that first value is pi over 2. This integral rate, or arctan, is just 0. So at the end of the day, my final answer is pi over 2. And in other words, the limit does exist, and we'd say that this integral converges, and it converges to a value of pi over 2. So the area bounded between this bear, let's think about that graph for a second. I think it kind of looks like the old Bell function a little bit. So that integral from 0 all the way out to infinity, forever and ever and ever, converges to a finite number, pi over 2. Wow, that blows my mind. But anyway, hope that helped get the rust off, and good luck on the next time you see an improper integral question.